Well, good morning, good afternoon, good evening, wherever you are. And today is Friday. Friday is Icon X Talks. And then really, it's great to have all of you here with us today for Icon X Talks. So my name is Jagadish, and I am a distinguished professor of physics at the Australian National University and also editor-in-chief of the Applied Physics Reviews. And I'll be serving as a moderator for today's talk. So as all of you know, that every Friday we have these Icon X Talks, and these are the speakers for July. And then last week we had Professor D.D. Sharma from Indian Institute of Science, Bangalore. And then today we have got Professor Anna Fontcuberta Morral from École Polytechnique Federale Lausanne, EPFL. And of course, you can see that other speakers are also there. And then really, we very much encourage you to come and join us and then be able to really listen to the experts in the field and then learn about what's happening and the most recent developments in those various areas of science and technology, which is really important for us. So today's speaker is a very distinguished colleague of mine and a star of the, in the area of semiconductor physics and semiconductor material science and technology, Professor Anna Fontcuberta Morral. And so we also have got today our, the challenger is Liu Sha from EPFL and from Microsystems Laboratory. And also we've got panelists, Professor Chen Rong and also Professor Chang Chi. And then they will be joining us after Professor Anna Fontcuberta's talk. And let me now introduce Professor Fontcuberta Morral. And then Anna has done her PhD from the master's degree from the University of Barcelona in physics. It's called as Diploma in Physics in 1997. And then she joined École Polytechnique in Paris and finished her PhD there in 2001. Then she moved to Caltech and then worked in the group of Professor Harry Atwater. And she was there for about 4 years. And while she was there, she has done some pioneering work in the area of solar cells. And even she started a company. And then afterwards, she returned to Europe again and then to Technical University of Munich as a Marie Curie Fellow. And then she started her own research group there. And then she has worked on nanowires there. And then she moved to EPFL as a professor. And then now she's a full professor and also the associate vice president for centers and platforms. And then really she has done a pioneering work in the field of semiconductor nanowires and applications of wide variety of applications as well. And really, it's a great pleasure and honor to have her here today with us. And then she'll be really sharing with us her recent work in the area of nanostructures and then using the 3-5 semiconductor nanostructures and also earth-abundant materials for a wide variety of applications. Please join me warmly welcoming Professor Anna Fontcuberta for today's Icon X talk. And I'm very much looking forward to her talk. Anna, welcome. And the floor is yours.
Thank you very much, Jagadish, for this very kind introduction. And also thanks to IconX and also to you for creating this kind of seminars. I think it would be difficult that we all meet together today, not because of COVID also, but and discuss about science. Well, today it is possible. So also this IconX is not only making it everything possible, but also low CO2 conference. So I'm going to talk today about
Anna, you're cutting off a bit.
Sorry, so somehow my Zoom quit, so hopefully it doesn't happen again. So I'm going to talk about compound semiconductors for photodetection and energy harvesting. Before I start, I'd like to give you a bit of a highlight of what I'm going to talk today. So I'm going to talk about several things, and I will talk about the relevance of the nanowire structures for the semiconductor applications. I will explain why it would be interesting to have compound semiconductors integrated on the silicon platform. And then I will finish with the transition to the earth-abundant compounds, all in views of photodetection and energy harvesting. In between, and because science has to be fun, I will just show you a fun finding that we had recently, just for the fun of it, so it will be in parentheses. So first, I will start with the relevance of nanowire structures, especially in photonics and in advanced applications. So first, nanowires are filamentary crystals with very well facets. And these facets make them excellent cavities for light resonation. So as you see here, if you include this in a cavity, in a plasmonic cavity like the one here, you can get nanowire lace, but not only lace, but to transmit the light in the plasmons that are in the gold and then emit it in the edge groove that you see here. Pioneers on this field have been Lieber, Beron-Yang, and Jagadish, as well as the group in the TU Munich of Jonathan Finley. Then also taking into account the morphology, which is this filamentary structure, one can think that the diameter is so small that if you have emission, then you would have the single photons, for example, they don't have any chance then to emit in the free space, which is not the case if you would have a single photon emitter in a thin film. So also nanowires have been used for ultra bright single photon emission. In the field of automechanics, they also use this large aspect ratio of the structures to use this movement for detection. And in this example here, what we showed is that a slightly asymmetric shape of the nanowires allows to sense electric fields in different directions and therefore map electric fields in a planar way. You could imagine that by having a magnetic nanoparticle at the tip of these nanowires, one would even be able to test and to map magnetic fields on a planar surface. Finally, it has been very largely discussed, and it's still today a large source of debate, is the use of nanowires for quantum computing schemes. And on the left, what you see is the use of the creation of Majorana fermions as a topological qubits for quantum computing, very well protected states that would allow a non-perturbed use of the qubits. And on the right, what you see is a very recent study from the University of Basel, in which they use holes in a germanium silicon core shell nanowire for spin qubits. So now if we move to the realm of optoelectronics, so what we see is, in fact, on the right, you see the mobility charge carrier of 3.5 compared to group 4, which are here. And what we find is that, in fact, these 3.5 semiconductors have a much higher mobility than the counterparts in group 4. They're also optically active because most of them have a direct band gap. So they're used for ultra efficient solar cells. As you see on the right, the best efficient solar cells is from Alta devices, and also for lasing and LEDs. Still on the left, you have the realm of electronics, which is silicon. All our computers are made of silicon because it's the most reliable technology, and it's also the cheapest. So would there be an advantage of having them do together, and what are the challenges? So if we look at the integration of compound semiconductors on silicon, what we realize is here's a cut on the 110 plane, and we look here at the 111 direction. The first thing we see is that the structure is very similar, but compound semiconductors are made of 2 atoms. So once we position epitaxially on the substrate, so the atoms will follow the same structure, and we want it to be as ordered as possible. So, but when we do this, if we don't do things well, what happens is that it may happen, like you see here, that some atoms of the same order are bound. And in a compound semiconductor, we need to have a group 3 element bond always with a group 5, and having group 3 to group 3 or group 5 to group 5 creates antiphase boundaries, and these are electronic defects that destroy the electronic functionality of the material. So this has to be completely avoided, and this is why, in fact, this has been the holy grail of optoelectronics, the integration of compound semiconductors on silicon. And in fact, in the planar realm, it has not been completely solved yet. Still in nanostructures, if we simplify the picture, we can imagine nucleating this material at a very small nanoscale. And because it's in a very small nanoscale, you don't have the chance to create these defects. And therefore, you get rid of these antiphase boundaries that really kill the functionality of the compounds. So if we now look on how we can obtain these compound nanowires on silicon, this is a mechanism that one can use. One can use a metal droplet to gather the growth precursors. And so you can use, here in this graph here, we use gallium arsenide as substrate, but it all works the same on silicon. You cover it with an oxide, a very thin oxide that will have some pinholes. The metal will go into the pinholes and accumulate from droplets, and these droplets will gather all the growth precursors, and upon precipitation, you will have vertical growth. So this is the skin, And I will show you later on how it works. So we rely, in the self-assembly, we all rely on very small pinholes. But there are ways of organizing this in a better way. We can use an oxidized silicon wafer with a very high quality oxide. And with even lithography or other nanopatterning techniques, we can define nanoscale holes and then etch them with reactive ion etching to get very well-ordered holes of the very precise size and location on a substrate. And the mechanism would go like this. You start with these holes, and then you deposit these metal droplets that will gather the growth precursors. The example here is for gallium arsenide, but you can have it the same thing with other compound semiconductors. Now, this scheme here is very nice to write proposals and to write a thesis topic, but when you go into the lab and do this, the first thing you find is this thing here. And this is a top view of this array, in which you see that you have some nanowires growing. There are filamentary crystals that are here. You have a lot of stuff in between, and they are not oriented as I showed here in this image. So in fact, it took us very long to find out why this was not working, why it works so well when it's self-assembly, and why it doesn't work that well when it has to be ordered. And I will tell you today what the mechanisms are and how you can achieve this with a very high yield. So we started looking at the initial stages because it seems to be that this is the moment in which things start to be going wrong. So we start with this thermal oxide, we position the droplets, and then we start looking at the initial stages. And this is a view from the top. So on the left, you see that these droplets are still, even though there is growth, you don't see anything because the nanowire grows and it's just below the droplet, and it's just in the shadow of the droplet. On the right, what you see is here, what we had is at the initial stage, the droplet was not well positioned in the hole, and this led immediately to nucleation on this side, and therefore you had a side growth of the nanowires, and you can already see it after a few minutes of growth. So what we want is very well positioned droplet. And what one has to consider is, in fact, when you start creating this droplet in the hole, you start sending some gallium atoms, and when they start growing, in fact, they start from the side, and they fill the droplet sideways. So you have to time very well how much gallium you see, that you fill it, but don't fill it too much, because then again, you will start having the droplet going on the side. But in fact, if we fill the droplet very well, as you hear on the left and the right, in fact, there are more things. We realize that that's not the full story. And that's why it took us so long to understand the mechanisms. So we saw that in some cases, even though the holes were very well filled with the gallium droplet and it was symmetric and all this, we didn't have vertical growth. So we looked again at the initial stages. We removed the gallium droplet and looked at the initial stages of the gallium arsenide growth. And this is what happens when you have high yield and low yield. So in the conditions of high yield, you have that you have planar growth from the start, or you have this circular growth that you have nucleation at the edges of this hole. And on the contrary, when you have a low yield, the nucleation of the gallium arsenide starts from an edge. And this is what fills the wire on the side. So it was very strange. So we try to understand why this happens and when do we have this tilted growth. For this, we looked at the role of the aspect ratio of these nanoscale holes. So we looked at this is the oxide thickness and then the size, lateral size. So we understood that it's not the thickness of the oxide, it's not the size of the droplet of the hole, it's the ratio between the two. And here in this graph, we compare the vertical yield for different aspect ratios of this hole. And we looked also at the reference 7, which is in fact a clear work, and which they understood that they found out that by changing the thickness of the oxide, they could optimize the yield. And in that case, it's because they always get the same size of the hole. So here we universalize this and show that is the aspect ratio. And you see then that by using different thickness of oxides and different size holes, we can get to the very high vertical yield. And this is what drives the very high yield. So you have here examples of very good yield of vertical growth. And this is absolutely reproducible when you prepare the substrate right. And if you don't do this, you see how similar growth conditions, or in fact, the same growth conditions lead to a full disaster. So trying to understand this, we try to understand what makes this asymmetry, what makes this nucleation at the edges of the hole that seems to help the vertical yield. So we looked at the cross-section here. In fact, when we start having the gallium droplet and then we send the arsenic is directional. And we realize that there is a shadow here, because when the arsenic comes here and there is the oxide, it doesn't go through. And this shadow here makes some gradient that makes the arsenic to diffuse on the corners and nucleate on the sides here. we simulated this and we realized how certain aspect ratios and give, in fact, to more shadowing and therefore to the nucleation at the size of these holes. So this was the explanation. After that, we were very happy because we understood how to obtain a high yield. And this opened the path to really start making devices on silicon and really doing more serious stuff than just nanowire growth. Now, everything I have shown you is on silicon wafers that are oriented 111. And in fact, today's technology is obtained on 100 orientation. If we do it on silicon 111, it's because these nanowires like to grow on the 111 direction. And therefore, if we use 110, we would have tilted growth. But we ask ourselves, can we try to engineer these initial conditions of growth to also get vertical growth on 100? And for this, we did a slightly different preparation. To get rid of this shadowing effect, we created pillars that we oxidized and we then filled the droplets on top. By looking at the given volume of gallium that we sent as a function of the pillar diameter, we could engineer the contact angle, which is very important to initiate the growth. And you here see examples of arrays of gallium droplets on silicon pillars that are made here. And you can see how they are very reproducible from one to each other. After doing this, we then understood that with a contact angle of 90 degrees, we can nucleate vertical structures. They are not really nanowires, we call them nanostates, but they grow vertically. And in fact, they have nearly single crystals. In fact, there are two crystals that are forming like this, and they have outstanding optical properties because of their pure phase and the lack of defects. So as you see here, the yield is not 100% yet, but it's the first step towards integrating these gallium arsenide nanostructures for photonics on silicon. So now I make here a small break, and I would like to talk about this fun finding. And this fun finding happened by just asking ourselves, how these growth happen. So it was just driven by scientific curiosity. So if you have here on the left the mechanism of nanowire growth, you have the nanowires growing here, you have in our case, the gallium droplet and the precursors that arrive, and some of them get dissolved in this liquid droplet, and they precipitate and combine with the gallium to form gallium arsenide. One of my students, Madi Zamani, he looked at the TM of these structures, and this is with an aberration correction TM, and he realized that in fact, the liquid-solid interface doesn't seem to be so sharp. Even at room temperature, there seems to be some blur, and he even intuitively saw some maybe order that goes further away. So the question is there a sharp transition from solid to liquid, or is the liquid order that comes solid at the interface, or does this affect the crystalline growth, and how does it do it? So for this, we started a collaboration with our colleague Michele Ceriotti, who is a fully theoretical professor, and he did machine learning to model the gallium potential, and therefore to understand how the gallium potential is perturbed, the potential of gallium atoms is perturbed in the liquid state when it's close to a solid. He simulated this, and then here you see here the position of the gallium atoms close to a surface of gallium arsenide. And we showed this for two polarities, for polarities of A and B, which means that you have either the gallium at the top, so this is the dimer of gallium arsenide, either you have gallium at the top or arsenic at the top. And we saw that this polarity really changes the order at the top, and he saw this with his simulations. He saw that the atoms on top of the gallium arsenide, they arrange themselves in 3 dimensions, nearly like a crystalline phase, but just gallium atoms and no arsenic. And that this order, if you look here, in fact, it explains why in one case, when you have bipolarity, it's very easy for the atoms, when the arsenic atoms comes to put in the position of one twin of gallium arsenide or the opposite twin of gallium arsenide. And this explains why we have a lot of twins in the growth of bipolar gallium arsenide nanowires, while in the apolar, there is only one position where the atoms can go. And there really, we don't have any defects. It's twin-free gallium arsenide. So by just here following our scientific curiosity and really using very advanced calculation methods, we could understand what happens in the interface and see that also it's not liquid is amorphous and solid is ordered. There's also an interface in which the order exists, and interesting things happen there. Now, I go to the next question is, do nanowires only grow upwards? So here is an example of nanowires grown by the group of Julie Lee. I think she also gave a talk in the ICANX talks. So here you see a top view of gallium arsenide nanowires growing horizontally. So also here you have this metal droplet that drives the growth in a direction. And you see how here they're oriented horizontally. And in some cases, then they choose to grow in the vertical direction. So the question is, are there other ways to grow them horizontally? Do we always need the droplet? And so what I would like to tell you today is that there are also other ways of obtaining it horizontally, and there are also advantages for this. So here on the left, you have the typical growth in which you have the metal droplet that drives the vertical growth. You can also use more droplets to grow trees. And also you can try to kill the droplet and make core shell structures. You can also try to see, like as I showed you before, you make holes in the silicon, oxidized silicon, and you can try to grow without the droplet by just growing like you would grow a thin film in this localized area. If you have a hole, you would have a vertical wire going up. But you can try to just make this hole long, and even in more creative shapes, as you see here on the right. And then you may not have vertical growth may be slower, and you may grow horizontally in certain directions. And that's what you show here in this scheme. So we tried this also to grow the nanowires horizontally, but also to use them as templates for more complex structures to have even other nanowires going on top. So this is for us a way to obtain scalable nanowire networks in which you grow a very large number of nanowires already on chip and ready to be contacted. And as you see here, you have plenty of markers so that once you have grown, if you go back to the EBIM, you can define all kinds of electrical contacts to make your devices, and you have like thousands and thousands of devices on chip. Here is an example of wires that have been connected in this way. And if you look in detail, what you see is that we can grow indium arsenide, like this is gallium arsenide in all these directions. We grow indium arsenide on top. The indium arsenide will go real at the top, doesn't like to wet the surface of the gallium arsenide, and it accumulates only the top, making a very high quality indium arsenide nanowire. In this case, it's indium gallium arsenide nanowire. And then you can contact and make devices. And in this case, we have used these nanowires for quantum computing schemes, and we have shown that we have a relatively long coherence length for the electrons that are flowing through these nanowires. But now, if we look at the photodetection scheme or light harvesting, what is better, to have nanowires lying on a substrate, or would you like to have them vertically? If we go back to the very pioneer works of Charles Lieber, we see that he looked at the light absorption and emission of a horizontal nanowire, and he looked at the polarization dependence. And if you look at these images here, what you see is the emission of light. When you have the polarizer along the nanowire, you have a lot of signal. And when you cross it, then you block all the light. And it's because this longitudinal shape of the wires makes it selective to polarization, both for the absorption and the emission. So you already see that you're losing half of the light. We can try to see if there are ways of getting around it. And my message today would be that you can use plasmonic structures to go around this. So one way to also measure the absorption in single nanowires is to fabricate contacts. So here you would have 4 contacts to measure 4-point contact resistance, and then measure the photocurrent for parallel polarized light and perpendicular polarized light. And what you see here is in a single device is that when the light is parallel to the nanowire, you have much more photocurrent generated in the nanowire because it's selective to this polarization. You also see this is a phenomenon that is brought around here. It's along all the wavelengths that this happens. You can try to couple plasmonic structures, and what you can see here is to change this symmetry. You can put some bow tie antennas, and by just putting one every micron along the nanowire, these nanoantennas, in fact, make the absorption in the perpendicular direction much more feasible. In fact, they collect the light on the perpendicular polarized light, and you can see how by just having 1 micron apart, you can completely reduce the anisotropy and light absorption by not reducing at all the photocurrent generated. And you see here when you put more antennas, in fact, you can reverse the anisotropy of the nanowire absorption. So there are ways of going around the anisotropy of the nanowires. Another example would be the example that Michael Johnson and Jagadish did recently, in which they use another plasmonic scheme, another plasmonic antenna scheme similar to the bow tie antennas, but much larger, in which they show how you can have cross nanowires that are not connected, but they're both connected to a bow tie antenna that is microscopic. And this allows you to resolve the polarization and the energy of terahertz pulses. And this allows you to do very interesting science. So this paper was published at the end of last year in Science. So now going back to this, I mean, maybe there are some photodetecting scheme in which the plasmonics help us. But if you want to have very large photodetection scheme, maybe you want to have something that doesn't require this plasmonic structure. So going back to these nanowires, how I explained you that they're very good light emitters, we can try to be inspired by this. So what you have here is, again, these vertical nanowires, and people have studied them in different shapes. So just vertical with no tapering, inverted tapering, or normal tapering. And they have seen how these structures really affect the direction in which the photons are emitted. And they have shown that if you have a back reflector in the back, you can really have nearly 100% emission, so collection of the light that is emitted by photons inside the nanowire. Now the question is, this is for light emission, but can we apply the same scheme for light detection? So the question is, you have here a vertical nanowire, and does this nanowire not only emit very well the light, or is it also inversible, the problem? Or is it also a very good structure to capture the light? And the idea would be, is it like a nanoscale lens that concentrates this light, or it acts as a funnel to funnel the light into the nanowire? So for this, we did a kind of experiment that is quite original in my sense. So we put the nanowires in a liquid solution with plenty of fluorophores. And here the fluorophores, they are there to map in 3 dimensions where the photons are. So we send some photons and in a wavelength, and the fluorophores emit below that wavelength, so that we can filter the incident light in the detection and see where the photons are. We use a confocal microscope, so like this, we measure the map as a function of z with a very high precision to see where we detect photons and where the photons are at all. So this is an example of this kind of measurement. So you have here the nanowire, the excitation wavelength is 633, and the detection is between the 670 and 690 nanometers. So when you make this, we can have here a z-plane in which we see how very far from the wire you have homogeneous light emission. So the fluorophores are homogeneously distributed everywhere, and so you detect photons independently of the z space. Once you get close to the nanowire, you see that you have very high emission close to the nanowire, and then you develop some kind of shadow. I will tell you later on why you have this high intensity here at the surface or close to the surface of the nanowire, and it's not due to a different distribution of the fluorophores. It's really due to the photon field. And then when you go down, somehow the photons disappear. So there are still fluorophores there, but they don't luminesce because photons don't get there. All the photons have gotten inside the nanowire. And if we make a cross section, for example, here you will see how you have this high intensity close to the surface of the nanowire, and around you have developed a shadow. So all the photons have disappeared, they have gone into the nanowire. We can run simulations and look at the effect of the diameter. And you have here 2 examples of 2 different diameters of nanowires. You see here the absorption cross-section, in which you see that the absorption cross-section is very different from what you would get on bulk gallium arsenide, and it's defined mostly by the shape and the diameter of the nanowire. So you have a peak here, and in both cases you have a peak in the red that depends on the diameter, and a second peak here. If we look now at these different points for the excitation wavelengths, we can see where the light is, and also the maps here for these different wavelengths. And what we'll see is in this high emission, let's look, for example, in these low emission, low absorption cases. So in these low absorption cases, if we look where the light is, so we see that there is no shadow developing here. In fact, the nanowire is absolutely dark. And if we look at the simulations of where the light would be, if the light would get into the nanowire, you see this as completely wave-guiding mode. So in fact, wave-guiding modes which intuitively would give light absorption because the light stays into the nanowire for a long time, in fact, give you very low light absorption. On the contrary, if you look at this high absorption peak here, you see how the shadow develops, as we said before, and you see that these are modes that live outside, partially outside the nanowire. These are called leaky modes. And the explanation here is, in fact, it's not enough where the light is inside the nanowire, it's about the coupling. And what we see is that the modes that live partially outside, the leaky modes, they couple very well to the incident light, while the waveguiding modes, they're very difficult to couple, and that's why they absorb so little. So this is the explanation of why these vertical wires, they couple very well to some parts of the wave of the light, and then once they are coupled in, they absorb very high the light, and so this makes it very good structures for light absorption. So if we now go from the photonics concept to the solar cell, then we can imagine then an array of wires here in which the light couples very well. We see that this light absorption, this favorable light absorption is quite broad. And so you can imagine this, it couples very well the light. You have this shadow where photons are missing, so you can space these nanowires at a certain distance and then have like an empty material that absorbs very well the light. And you would have an electrode at the top that is transparent to collect part of the photogenetic carriers, and then the substrate would collect the others. So now after seeing this, we have to see what is the optimal diameter for that. So we did some simulations looking at the optimal diameter for the 2-micron gallium arsenide nanowires, and we looked at the absorption rate when you illuminate them with one sun. So you see here that depending on the diameter, you have very high absorption rates for wavelengths that are close to the band gap. And this is exactly where there is the peak of photons in the sun. So it's quite good that we have a high absorption rate here. Still, we don't know if this absorption rate is high enough or if it's higher than the photons you see. So you need to compare to the incident rate of photons. Once you do this, you can deduce the absorption cross-section, and what you have here is the diameter of the cross-section. So you can imagine this cross-section as the diameter of this shadow area that develops in the nanowire, this area in which the photons disappear. And we see that for the ideal diameters, it can go up to 3 times the diameter, so 1200 nanometers for 380 nanometers nanowire. So it shows that you have a nanowire here, and all these regions here acts actively for the nanowire to absorb the light. We applied this to a single nanowire solar cell. At that time, we still didn't know how to obtain arrays of nanowires as ordered that I just showed you before. So we created a P-type beryllium doped core, and then an intrinsic shell, and again an N-type shell. And we then make a single nanowire device in which the bottom contact would be a very highly doped silicon substrate, and the top would be ITO. We then measure the current voltage characteristics, and you see here the characteristics in the dark and under one sun. And we see that we create a photocurrent that is 180 milliamps per square centimeter, which is it's about 3 to 4 times one of the best solar cells. So here we create a very high amount of photocurrent, and it's because we collect photons that are around the nanowires. If we normalize to the lateral size of the nanowire, this gives us a very high current density. If we now transform this into the external quantum efficiency, which is how many electron hole pairs you get by nominal photon getting into the nanowire, then this gives you that when you have a vertical wire, you have 15 electron hole pairs generated by nominal incident photon. And if you have the same wire horizontal, you have much less. And it's because when the wire is horizontal, you collect much less photons than when it's vertical. When it's vertical, you have all these photons that come around and funnel inside the nanowire. So where does the field stand today? So other groups also realized the same as we did. And so in Lund, they've had the first demonstration of a solar cell optimizing the distance between the nanowires and the diameter that was close to 14%. Later on, they moved to 15.2%. And on collaboration of the T. Eindhoven and Amolf, in fact, they went up into the efficiency 80%, but they also developed much more the theory of why having this sort of funneling of the light inside the nanowires helps increase the open circuit voltage of the cell. And this, in fact, if you would have a perfect cell, this would help you go beyond the Schottky-Queisel limit in efficiency because of this increase in open circuit voltage. So now that I show you that 3/5 and nanowires give you the potential to have very high efficiency solar cells, and now we start I would like to ask another question, which is, should we worry about dependency of elements? So this graph here shows you the abundancy of elements in the Earth crust. You see the elements that are much more present would be the rock-forming elements that you find here, like iron, silicon, aluminum, sodium, manganese, magnesium. And you have others like the indium, which is very scarce, very close to the rare earths. This is the rarest metals that you can find. You have gallium, it's a bit better, zinc, better, and phosphorus is even better than. So if you look at indium gallium arsenide or indium phosphide solar cells, you should worry that maybe if you want to use it, solar cells, which means it's applications which you need a very large area, maybe there is not enough elements on the Earth to make efficient solar cells for everyone. So if you want that everybody has access to this technology, we should probably worry about using elements that are much more abundant. So why do we do this? So we all have heard about the need of defossilizing energy systems. So this study here, you can go and look at it. It tells you, so what should we do to avoid to go to the 1.5 degree increase in temperature in the next years? And in fact, if you look at what CO2 emissions we have already emitted, it tells you that in the next 5 years, that's all we can emit in the atmosphere if we want to avoid this 1.5 degrees increase. Certainly, if we emitted all this in 2020 with the COVID crisis, certainly we will not be able to do this in the next 5 years. So they looked at what are the alternatives that we have to reduce the CO2 emissions. And so they made a very broad analysis of what all the energy sources in the world, and they made to the conclusion that this should be the distribution between all the sources of energy, and solar is really a very big part. And so we need to find ways of making solar cheap and easy to fabricate at large volumes. Here you see here, they also analyze as a function of the countries. Of course, Australia is very well situated in terms of energy, solar energy. It's probably one of the best countries to live if you want to live from solar cells. So the rationale to go beyond photonics, and I showed you that with nanowires, we can reduce the consumption of material, in fact, a factor of 1,000. So if you look at the best solar cell will use gallium and indium elements to fabricate it. This would be a multi-junction solar cell. So if you imagine that this is a very expensive device, like similar to a very expensive car, then if you do the same concept and use nanowires, you reduce by a factor of 1,000 use material consumption, which means that the price could scale also. And so it means it comes to a price of very expensive earrings, which maybe are easier to buy for the normal people. Now let's go a step beyond and see that can we do it now with very available materials that are not so expensive as indium and gallium. And so then maybe if we do a further reduction of factor of 1,000, then a solar cell would then be reduced to the price of what we spend on groceries every week. So maybe this would be a good thing so that we all can collect the light on our garden or on roofs. So for this, we then need to go to material selection and see what materials are there to do this. And so this study here looked at different compounds and different materials and looked at the annual electricity potential index and the extraction cost index. So how much material is there and how much electricity it takes to extract it. And please note that silicon is here in the center. And the best quadrant is the one here on the right. So there are many materials that are even better than silicon. Iron sulfide is the best, although it has been shown that it's very challenging to have very high quality material. And others that are better would be, for example, zinc phosphide. And I will concentrate on zinc phosphide today. What we've seen is that with gallium arsenide that is in the wrong quadrant, in fact, by reducing the size, you can put it up. So you can reduce the annual electricity potential index, because with the same amount of material extracted, you can increase the amount of energy you can produce. So zinc phosphide is a material that has a very complex crystalline structure. It's a tetragonal crystal structure with many atoms in the cell, a very big cell, with a direct band gap around 1.5 electron volts, which is the right band gap we want for solar cells. Minority carrier diffusion lengths are long, and the absorption coefficient is very high. the challenges in this material and why people didn't try it before is because there is no substrate to grow it on, and it has a very large thermal expansion coefficient, which means even if you can grow it on a substrate at a certain high temperature, when you cool down, it will crack. People couldn't achieve doping and heterojunctions in the past. So we decided to go to this, to solve these challenges first, because material science has evolved since people tried this before. And we know the advantage of nanostructures, so we'd like to utilize the advantage of nanostructures to work on this. The first thing we did is we tried to grow on graphene. And using graphene as a substrate is because if you grow anything on top, you will not have any covalent bond with the graphene, because in graphene, all the covalent bonds are in the plane and not outside the plane. And so with this, you would allow that you grow a crystalline material on top. There is no lattice mismatch. And even with the thermal expansion, when you have different expansion of contraction of the material just floats on top of it. So you will not create any cracks. So for this, we used the commercial graphene on silicon from the company Graphene. And the mechanism goes as this. These commercial graphene substrates are not single crystalline graphene substrates. They are polycrystalline, so you have several grain boundaries and some point defects also. And we use this as a way to nucleate the material. Because if you have a pure graphene, you would not have any attachment of the atoms that come to the surface. So we use these defects to nucleate the film and start growing laterally. So when we do this, you see how in the initial stages of growth, you have how the grain boundaries, the some point defects are the initial points where the layer starts to form. You see that some of these crystals that are formed are in the same orientation. So when they join, they will create a high crystalline layer. We also then looked at the advantages of the nanoscale and growing nanowires. And so for this to reduce the potential of doing defects. And I will show you two ways of doing this. First, by growing nanowires, and first by just using nucleation at the nanoscale for then growing thin films laterally. So this is the example of zinc phosphide nanowire arrays. By just controlling how we treat the surface and the fluxes and temperatures, we were able to grow a very high density of zinc phosphide nanowire arrays, as you can see here. And what we also realized is this compound is quite different than 3,5 semiconductors. In fact, the stoichiometry in 3,5 semiconductors is very fixed. For every element 3, you have an element 5. For zinc phosphide, for the 2 5s, in fact, you can vary the ratio between the element 2 and the element 5 because they change the oxidation state. And this gives you different properties in the absorption coefficient. So you see here, by just changing the ratios between the zinc and the phosphorus, we can get different compositions in the nanowires, and we can control this by just the growth conditions. We then looked at the optical properties, and this we did by exciting the luminescence with a cathodoluminescent microscope, the Atolite photoluminescent microscope, and we measured the luminescence, and you see how depending on the ratios that we use during growth, we can shift the luminescence peak quite a broad range here. So we can change the optical properties by changing the composition, which is quite strange if you're used to normal compound semiconductors. We also measured, in collaboration with Ilaria Sardo in Basel, we looked at the absorption coefficient, and we compared to other compound semiconductors. So for this, in fact, they put a nanowire on an apparatus that is suspended and then measures temperature changes. So they measure the absorption by measuring the temperature change into this thermometer that is here. And what they realized is, in fact, the gallium arsenide, and you compare gallium arsenide and zinc phosphide, which have very similar band gap. In fact, the absorption of gallium arsenide is 5 times lower than zinc phosphide. So zinc phosphide has 5 times higher absorption coefficient than gallium arsenide, which means that you even need less material to make a solar cell. We also looked at the absorption coefficient by energy electron loss spectroscopy. So we went to the SuperSTEM facility and looked at how we illuminate the nanowire with the electrons, and we look at the loss of this of energy of these electrons in the material. And we looked at nanowires that have this zigzag shape, and we looked at how this spectrum looks close to the nanowire, to the edge where the nanowire is super thin, and in the center of the nanowire. And with this, we excite different kinds of plasmons and different kinds of transitions. And as you see here, so we see, in fact, what we see, this is the nanowire we looked at. And so by comparing the two geometries, we see that in the Gracie incidence geometry, we're able to get the absorption coefficient close to the band gap, and we're able to resolve all this high absorption, and we see how there is a very high absorption just after the band gap. And this, in fact, to interpret this, we simulated the band structure, and this gave us the understanding of why this material has such a high absorption coefficient. And in fact, it's because in the conduction band you have several bands piled on top of each other, which gives you very high absorption. So now we went on and utilized this nanoscale nucleation to really now maybe instead of having nanowires going to textured thin films. So we started again with a substrate that has some pattern, and we started growing on these nanoscale patterns here. So here you have the growth after 5 minutes. So you have these small grains that are formed inside. And if you are a material scientist and you start seeing growth with these multi-layers, these multi-nuclei, you would think this is never going to work. This is going to give you a polycrystalline material. It's not going to work at all. So if you look at the function of time, you see how these, in fact, they merge and they form a very well-faceted crystal. And you see here how at the end it creates a pyramid, and when the holes are very close together, then they merge, forming, in fact, a textured film that, in fact, traps very well the light. So this would be now a thin film that we would use for the solar cell device. If we now look at the cross-section TM, we see that, in fact, even though the growth starts with a small nuclei that are not connected to each other, in fact, when you grow one of the simple pyramids, it's a single crystal. And somehow the material arranges in a way that you create a very perfect crystal. And this is now what we want to use for solar cells in zinc phosphide. And for us, I think this is the highest potential material for Earth abundant solar cells. Well, here you have one of these textured layers, and you see how you have some interface of the grains that form of the pyramids that join at some point, but they don't seem to perturb the optical properties. And so this is the thin film that we have formed by this textured growth. We then look at the optical and electrical properties. So also here we looked at the effect of the fluxes and also how we prepare substrates in the zinc to phosphorus ratio. And we also saw that depending on the hole size that we do on the substrate, we change the ratio between the zinc and the phosphorus, which changes the optical properties of the zinc phosphide. If we look at the luminescence, this is the luminescence of the substrate, and this is the luminescence on the zinc phosphide. This is a very high luminescence that we get from these layers, even higher than for the nanowires. So this illustrates how this is now a very good way of producing high quality zinc phosphide layers. Here in the middle, we looked at the electrical properties by growing the zinc phosphide on P-type, N-type, and intrinsic substrates. We see that the intrinsic substrate is a Schottky behavior. With the P-type also is a Schottky behavior with lower resistance, while on the A-type we have a diode-like behavior, showing that the zinc phosphide is P-type, as we would expect from the previous studies, and opening the way to creating p-n junctions and solar cells. Now, if I summarize what I present you today, so I have hopefully conveyed to you that photonics and material science approaches help us tackle some sustainability issues, and that nanostructures provide a way to save resources due to the size, but also to the photonic properties, and that novel properties of nanostructures and new materials provide new paths for energy conversion and photodetection. For this, I'd like to thank the students in my group. They're really very hardworking and very creative. I'm very thankful to be able to work with them. And also to the collaborators, I'm very happy to be able to collaborate with such nice people and so smart people. So thank you very much for your attention. I'm here opening for questions.
Thank you, Anna, for an excellent talk and very creative work, and so really impressive work on what you have been doing. And so generally we try to keep the number of questions limited so that we can have the panel discussion. And one of the questions is from Cheng from Fujian. A wonderful talk. I am wondering, the aspect ratio is one important parameter for the nanowire solar cell. Also, the density and uniformity of nanowires forests are important too. Can you comment on this?
Mm-hmm. So that's a very important question indeed. So for light absorption, it's important the diameter. So you should choose very well the diameter, and you have a bit of tapering, then you would increase the broadband absorption. Then for the aspect ratio would be the ratio between the diameter and the length. So for the length, what is important here is it's much less important for light absorption, but more for device fabrication. If you have too long nanowires, then you would have higher absorption, you would be able to space them more, but then what will happen is then the fabrication, they will break. So mechanical stability is an issue. So 2 microns is quite good to make devices and not breaking them. Then for the distance, then you need to calculate, you need to run simulations and understand what is the ideal distance so that you absorb all the light and that you don't have light going to the substrate. Still, if you make dual junction solar cell, so if your substrate is also a solar cell, then it doesn't matter too much. We have shown how you can, in fact, it doesn't matter too much because the light that is not absorbed at the top will be absorbed at the bottom. So it's much less important the distance there if you have a dual junction solar cell. What is, if you want to make a high efficient device, what is really tricky is the contacts. And because of the mechanical stability of the device, in fact, if you don't have a super clean room facility, it's very easy to have a leakage in the structures. So here it's really, really difficult you need really a lot of nanofabrication support to have a very efficient device.
Good, thank you, Anna. And the next question is from Chen from Chengdu. And then he's asking, it's a great talk, Professor Anna Fontcuberta. And so in the case of zinc phosphide nanowires, you seem to have got some sort of a superlattice structure. Is it a twinning superlattice or some other structure? And can you please comment on that one, please?
Mm-hmm. Yes, so it looks like the twinning superlattice structures that we see with the 3-5. There is no twin, and because in this tetragonal structure of the zinc phosphide, there is no twinning possible. Twins don't exist. But what happens is we have this triangular facility, which makes that the wire increases the diameter and the droplet ends becomes unstable. And then energetically, it's more favorable for the structure to just change the direction. And because it cannot twin, it creates a layer rich in indium. And then it grows into the other direction. It's just the mechanical stability of the droplet that creates this churning every so often. And the period is inversely proportional to the diameter. So the smaller it is, the higher the period you have. But yeah, the regularity is quite good. So it's like a superlattice structure. Just it's not twins. It's this interlayer of indium that you have in between.
Okay, thank you, Anna. The final question is from Lee from Xiamen. And so why zinc phosphide has got a higher absorption than gallium arsenide or indium phosphide?
Yeah, this is also a very important question because it's quite astounding. We have simulated the band structure of zinc phosphide, and in gallium arsenide you have the valence band and then the conduction band, and these transitions gives the light absorption. So in zinc phosphide you have here the conduction band, you have several of them. And so you have many transitions possible because on top of the bottom conduction band, there are others in which the transition are possible. And they're relatively flat, which means that the density of states is high. So you have a lot of transitions possible to make light absorption. That's why we have a higher light absorption.
Okay. Thank you, Anna. And generally, we try to keep the questions to 3, though there are many questions. And so basically, so that we can have some panel discussion. And thank you very much for a great talk and a really fascinating talk and also answering those questions so nicely. So now let me welcome our panel members. And as I mentioned to you that we got wonderful panel members today. And let me introduce Professor Rong Chen from Huazhong University of Science and Technology, HUST in Wuhan. And Professor Chen has done pioneering work in a wide range of fields. And she has also led many projects and then has published more than 130 papers. And she has won many awards. And then really great to have her here. She's a full professor in HUST. And then please join me to warmly welcome Professor Chen.
Hi.
We also, welcome, Professor Chen. We also got Professor Chi Zhang. And so he is from the Beijing Institute of Nanoenergy Nanosystems of Chinese Academy of Sciences. And again, he's another star. And then he's again principal investigator of the Tribonics group in the BINN. And he has published 130 papers, and his work has been cited more than 5,000 times. He's got H index of 42 or so. and he's really doing beautiful work on nano energy and nano systems also. Please join me warmly welcoming Professor Chi Zhang as well. Then finally, we've got welcome. And finally, we've got our challenger and Dr. Sha Liu from EPFL and from the Microsystems Laboratory. And then she has done her PhD from Tsinghua University, and then she has worked in Case Western University and then moved to EPFL. She is a research scientist there, and then she has published 20 papers, and then she has won the first prize for her PhD thesis from Tsinghua University. And so she is a rising star. Okay. So really great to have all of you here. Thank you very much for joining us. And so at this late evening for you. And so basically, we generally give the opportunity for our challenger first, and before inviting other panelists to really ask questions. And our challenger, Dr. Liu, would you like to ask a question to our speaker today?
Yes, thank you for your kind introduction. And now could I ask you a question about the gallium arsenide? Have you considered any doping in this nanowire? Maybe it can increase efficiency in the energy harvesting. This is my idea. I don't know. Have you considered any doping?
So yeah, we have investigated the doping of the nanowires for creating the solar cells. You can do solar cells without doping by just having selective contacts of electrons and holes, but otherwise the traditional way would be to dope P and N type to create a diode. Other ways of increasing the absorption with doping would be to include rare earths or other things that would create other effects to increase absorption. So these other paths we have not investigated. We have mostly investigated the doping for creating the devices. And in fact, we published a review in Applied Physics Review, edited by Jagadish just recently, in which we explain how doping can be achieved and what are the challenges.
Okay, thank you for your answer. And one more question about the diameter of this nanowire, because I had some experience in the devices. So I'm thinking for the future, of course, for the nanowire-based energy harvest devices. So you are going to use nanowire forest these devices. Have you considered the density of the nanowire and the diameter of single nanowire? Have you any trade-off between the density and the diameter of this single nanowire?
Yeah, there is a trade-off between the two because you want to optimize absorption, but also to optimize absorption in the single nanowires, and they have to be very far apart, but you don't want to leave any light going to the substrate. So we have shown what the optimal is, and so it is a bit closer than the diameter of the absorption cross-length. And yeah, we have calculated this, and typically what we do is we do FDTD simulations of the arrays and vary the distance to understand what is the ideal distance and the ideal nanowire. So this all has to be supported by simulations.
Yes, I agree. Thank you for your answer.
Okay. Dr. Liu, while we'll come back to you, you can also ask questions about the career and other things as well. You don't have to ask only technical questions. Please think of anything which you would like to ask as well. And so don't feel shy to ask questions other than technical questions as well. Okay.
Okay. Can I ask now? I can ask.
Sure, you can ask. Okay, go ahead. Go ahead, Dr. Liu. Yeah.
Okay. Yeah. I have a question always in my mind. So for our young scholars, so can I ask how can we have a smooth transition from postdoc to AP to assistant professor, because this period should be very difficult for a young scholar. Do you have any advices for us?
Yeah, it's probably one of the most difficult parts of the career. Even when you have a position, you have to work very hard because you move place, you create a new group, you are learning to supervise students. Your difference age with the students is not very high. They have to respect you as a boss, and also it might be that you also have small children, so this also makes you more tired. So it is probably one of the most challenging times. But you just have to think that you have to understand why you like this job, and usually for me what works is curiosity and the love to work with young people. and then, motivated by this, see that this difficult period passes. So there is a point in which then things go much smoother. So you just have to stay on and know that it's not going to be as hard as it is at the beginning.
Yeah, thank you. Yeah,
so have faith in yourself, and keep the fun.
Yeah, you're right. It's always, the curiosity will keep you have a lot of passion, and so you can start your career and have your own life. Thank you so much for your comment. Yeah.
And don't forget about keeping the private life. It's very important. If you're not a happy person, you cannot be a good scientist.
Yes, I agree. Yeah, thank you.
Okay, thank you, Dr. Liu. And maybe we'll go to Professor Chen now. And Professor Chen, do you have any questions for the speaker?
Yes, first, thanks, Professor Jagdish, for the nice introduction. And of course, thank you very much, Anna, for this great talk. I really enjoyed it. So I have a couple of questions. The first one is about actually the controlled nanostructure, because in all your talks, you talk about utilizing this compound semiconductor, and you made a lot of beautiful shapes. So my first question is that can this be fabricated with high crystal qualities? Are they fragile and easy to be integrated? Because a lot of this for the applications, either for photo detections, energy harvesting, etc. So my first question is, are they fragile and easy to be integrated?
So the reproducibility is extremely high. With epitaxy techniques, you have a very high reproducibility rate across the wafer, and they're identical to all of them. And by understanding the mechanisms, you can make them very high quality. So this is the first thing. Then for the devices, for normal transport devices, like the ones we use for quantum computing, they're absolutely reproducible, and there is no issue because they're horizontal to the wafer. Now with the vertical wires is a bit more challenging. And in fact, what we see is that, the groups that have achieved the highest efficiency, these are groups that have professional clean rooms. Like, for example, Eric Backers in TU Eindhoven, in fact, he does the fabrication with the old clean room of Philips. And so you have a company behind, and you really have the required technology to do this in a proficient way. I think in a clean room of a university, even if at EPFL have one of the best clean rooms in Europe from the academic point of view, we're still not there yet. Also in Lund, they also have had companies to support the solar cell development. So I think here it's very, very tricky to do it all yourself in the lab. I don't know if I answered the question.
Thank you very much for the great insight. So my next question is related with the selective area epitaxy. I really like that because my background is more towards atomic layer deposition. Sometimes we use the epitaxy to achieve the selective area deposition as well. So my question here is that could you comment on the thermal budget and the speed for the epi? Because I personally, because I'm more like towards the semiconductor background, so I'm really interested to see this kind of process and wonder whether this could be integrated in. So whether you could comment on the thermal budget and the speed for the epitaxial process itself.
Mm-hmm. So if I would integrate these materials in the semiconductor industry, I would probably use MOVP or really techniques in which you use a very high flux and of precursors in the gas phase. So I wouldn't use molecular beam epitaxy, because molecular beam epitaxy, to do one of these structures, it may take us, so including the charging and all this, it's 1-2 hours. So it's too much. Mm-hmm. If you do it with MOCVD or a similar technique, you could even imagine a roll-to-roll way in which you can have a much higher throughput. You can decrease the growth by a few minutes instead of hours. And so this becomes much more advantageous. So if I would apply this to industry, I would not use molecular beam epitaxy, I would use MOVP or something that it goes much, much faster.
Yeah.
In fact, Alta devices, in fact, that's what they use. They use a high throughput vapor growth technique. And I think they grew 1 micron in 1-2 minutes. And this is thin film growth, so it's super, super fast. So I would use something like this.
Great. That's really look forward to see this kind of bottom up and controllable for the direction. It's such wonderful. So my last question is relatively quick. It's actually, you talk about the photovoltaic and it demonstrates a really great properties. That is from the light to electricity. So if you utilize a similar type of structures to create LEDs, basically the electricity goes to the light emissions. Could you comment some on this? Because you know, like Wuhan, we have the optical valley and we have a lot of this kind of applications like LEDs. So I just want to hear your experts' comments on that.
Yeah, thank you. Yeah, so it is quite symmetric. So what can be a very good light absorber is also a very good light emitter. Depending on where you want to have the light emission or lasing, you should also tailor the diameter of your material. But in fact, these structures are perfectly suitable because in fact, if you have an array of wires, the emission is super bright because it doesn't go into the substance; it's all emitted into the vacuum. In fact, and so this is in fact, and there have been companies showing this. There has been the company from Lund showing that gallium nitride nanowires can be extremely bright. I think at the end they had to stop, not because the LEDs were not bright, but because they were not able to make them cheaper than the thin film LEDs made in China. So it was more of a price issue than of an efficiency issue.
Thank you. Thank you very much.
Thank you, Professor Chen. Thank you, Anna. And maybe let's go to Professor Zhang from Beijing Institute of Nanoenergy Nanosystems. And Professor Zhang, do you have any questions to our speaker today?
Thank you for Professor Jagdish for the introduction, and thank you, Professor Anna, for the great talk. And I'm very, very impressed that you have synthesized the nanowire semiconductors for the solar energy convention, and you have also selected the Earth-abundant elements such as synthesized phosphide. So my first question is, compare with the current elements such as the silicon, indium, and gallium, whether the performance is comparable or outperforming. And for your elements, what about the mass production problems such as cost?
Mm-hmm. Yeah, so thank you for the question. So the efficiency of these devices is still an efficiency of a device fabricated 30 years ago with the old technology. And they obtained something like 4%. But this is really 30 years ago. With these new materials that are much better, we haven't been able yet to fabricate a solar cell. We're doing it right now, but we didn't do it yet. We're on the way. So first we optimize the material, and now we're going to the fabrication of the devices. What was the next? For mass production. So mass production, again, I wouldn't use molecular beam epitaxy. I think this material seems to be so good in the grain boundaries. The grain boundaries don't have a good recombination. We have seen, in fact, we did pump probe terahertz measurements in which we measured the mobility of the zinc phosphide, and we saw that the ones that are even polycrystalline, they have very high mobility. So I would probably use sputtering to fabricate this material and not even MOCVD. So probably sputtering of zinc phosphide would be really the large area technique to create large areas of the solar cells, extremely cheap, much cheaper than silicon or even amorphous silicon.
Thank you. And my second question is about the energy harvesting. Also, you have demonstrated the semiconductors for the solar energy convention, and my research is focused on the mechanical energy harvesting. So, how do you evaluate the development prospects of the solar energy harvesting, and with nanowire semiconductors? And what about your opinion and the prospects for the self-powered devices based on the abundant environment energy harvesting?
Yeah, so I think we need all kinds. I think in the few years we'll already start needing all kinds of harvesters of energy, because what burning coal will at some point will not be an option anymore. So we will have to really get energy from all sides. So mechanical harvesters will be important, and solar will be important. And we will need all of these technologies to survive in our level of living. For the solar, cell devices that are self-sustained, you need. So we'll probably need the two. And the light ambience, in fact, when you are in a room in the night, let's say like Jagadish, he's at night in Australia, it looks like light is very bright. But in fact, if you compare the light, ambient light and the sunlight, it's about more than 1,000 difference in intensity. So the amount of power you can collect is not a lot. Of course, it's good to collect it and to not lose it, and having very cheap collectors makes this possible. But I think it's only possible in this case with very cheap light collectors, because there's so little power that you can collect that if you do it with an expensive cell, it's not worth it. Did I answer the whole question, or there's something still missing?
Yeah. We are very looking forward to harvest the energy, electrical energy very easily. Okay, thank you very much, and looking forward to your more exciting work.
Thank you.
Okay, so I think we'll go back and then ask our challenger if she has any questions. And Dr. Liu, do you have any further questions to our speaker?
Yes.
Please,
maybe you can ask a question not related to your talk, maybe about EPFL. So I has been EPFL for 3 years, and my advisor Jürgen Brugger, and he told me like in EPFL for faculty you need 3 things to do. One is teaching, one is research, another one is startup company. So teaching and research, of course, we know it how to do it. But for startup company, it's quite new for me, especially my background is from China, and so I want to know if in the future maybe I will consider it possible I can consider startup company in China. So how can we make a startup company successful or survive? Because we're scientists or professor, we're not like a business man something. So how can we make it survive or like beneficial something?
Okay, this is a long answer. So so at EPFL, so there are these 3 pillars: education, research, and innovation. And what we are supposed to do, we have to excel in 2 of them. We don't have to excel in all of them, but in 2 out of the 3. So either very good teaching and very good research, or very good research and very good innovation. So you can choose which ones you excel, not the 3. If the 3 is, I would say, I don't know anybody that excels in the 3. It's very difficult. Then for starting a company, so I started a company when I was a postdoc, and I did it again for the fun, because I thought it's an exciting opportunity, and also because at Caltech, every professor was starting a company. It was really in the culture, everybody starts a company, you have venture capital coming to the place and looking for ideas of professors. So it was really in the air, and it was very easy. So I thought, it's very interesting, so I will try this out. And then it turned out that I learned a lot, and I learned a lot about things that I could apply later on my research, because I had to create a group. We had to create the team of people that could start a company. We had to build a clean room from scratch. We had to create a lot of things from scratch. And it's very similar to starting your own lab. So this is what I learned. And then to do it, you have to have a very good idea, something in your research that you see how it can be useful for a product. And important, you should not become the CEO. The CEO should be a professional person that knows business. Because as a scientist, you're very interested in scientific ideas, but the CEO will make sure that you make money with these ideas. So these are 2 different roles: the science and the technical aspect. You need to find a person that you complement very well and that knows how to earn money. So then if you have this team, then you can make a successful startup. And then the last thing is there are a lot of courses in EPFL to learn all these things. You can look, there are courses at the Innovation Park. There is InnoSwiss that goes and makes a semester courses there in the evening. I think it's 1 day per week. and they teach you all these things of how to do innovation and how to excel in innovation. So if you're interested, you can take these courses.
Okay, thank you. And maybe one more question about
the
IP. For example, if I found a very interesting phenomenon and I obtained very good data, maybe I can write a paper. But I'm thinking when we should consider to write a patent to protect the idea.
Yeah, this is a bit. So you have to think about: is this something that could potentially lead to a product? And sometimes it is difficult because sometimes you don't have all the framework, and so maybe the information you have today, you think, no, I will not create a company with that. There is no way. And then a year later, you say, oh yes, there is this. So you have to maybe brainstorm with your colleagues and with your professor. Is this something that can be technology important later on and should be protected? And what you can do is you can protect the ideas with a preliminary patent, so just a priority thing, so that you can protect it for a year and a half, and this gives you the time to publish it and decide if you really want to pay for the patent or not. So this is what you have to do, and then you need a very good patent writer to help you, because there are certain rules to write patents that they really protect your idea. And also, we scientists, we are not educated for that. So you need a very good patent writer.
Yeah. Okay. Thank you. Yeah, we are working on that. So yeah, your suggestion helps a lot. Thank you. Yeah.
Good. So Anna, maybe I have a question for you. So you have worked in multiple countries, and they have really adopted to multiple cultures. And so also that you also support young, females, young students through Wish Foundation, mentoring them. And then what has been your challenges in terms of being a women academic? What challenges you faced in terms of being able to reach to this pinnacle of your career now? And I'm sure that there is, in fact, even a much more bigger and better things are ahead of you. Can you just tell us about what's been your experience has been and what advice you would give to young women, students and scientists, those who want to really pursue academic career?
I would advise to try to see who can mentor you. A mentor, mentoring, it doesn't mean that is someone that follows you all the time, and that is someone that accompanies you all the time in your career. A mentor, you can have a mentor with someone that just go to have a coffee in a conference and gives you good advice. So try to see in the community who can give you good advice and get it, and try to understand how people have success and the kind of success you would like to have, because there are many versions of success. So success is multifold. So see what kind of success you want to have and see how these people achieve that, and be curious also with them and communicate with them and network. Because I would say this is the most important. And I think maybe female scientists are a bit more shy than male colleagues, and sometimes it's a bit intimidating to enter a room and it's all male scientists, and sometimes maybe the average age is much higher than yours, and this can be intimidating. But yeah, I would say put a smile on your face, and then things will become less intimidating. And I see you already put a smile, so that usually works, because you look happy, then people look happy, and then things go better. So I would say this would be my advice.
Okay, thank you, Anna. And any further questions or comments? Well, if not, and so please join me in thanking our speaker and Professor Anna Fontcuberta, Morral, for giving such a fantastic talk and then really participating in the panel discussion and then answering all the questions. And also our panelists and our challenger, Dr. Sha Liu, and then also Professor Rong Cheng, and then Professor Chi Chang, and for their wonderful contributions to this Iconics talk and then panel discussion. It's been very interesting panel discussion. And then Anna, we would like to present to you, if you would have been here, we would have presented a plaque in terms of thanking you for your participation in this Iconics talk and sharing your expertise and knowledge. So we really want to sincerely thank you. And then we would like to present to you this particular, virtual plaque. and then hopefully we'll be able to really present you in person one as well. So now next week we're going to have a speaker, and then of course this is the next week's talk on July 23rd, and Professor Johanna Stackel from University of Heidelberg, and then she's going to talk about exploring Big Bang matter with collisions of heavy nuclei at the Large Hadron Collider. And she's really world-renowned expert in this area. And then again, you can see the panelists, and then my colleague, Professor Mahananda Das Gupta from the Australian National University is going to be the moderator, and then we'll have various panelists. And then next week's challenger is Bao-Chi Fu from Peking University, and then Hui Chao Song from Peking University is another panelist, and also Jin Zhu from Beijing Planetarium is going to be another panelist as well. Hope you are able to join us next week, and we very much look forward to seeing you next week. With that, and I want to thank all of you, all the supporters, and then also our background team, and of course the starter of the Professor Alice Sang, and who is the one who really started this IconX talks, and then her motivation is to really promote science and also promote scientists. And she wanted to make scientists as the superstars, and we can see that our speakers and panelists are superstars, and then really it's main, and also share the excitements of science. So thereby that will hopefully inspire the younger generation, and then feel motivated by these talks, and then feel that, okay, science is a career which I would like to pursue. With that, I want to thank all of you for participating in this today's talk. And also I want to thank once again our speaker, distinguished speaker, and also our distinguished panelists as well. Thanks a lot. Enjoy your evening, or the morning, or the afternoon. Thank you very much. Bye-bye.